At the moment, we can't possibly start a program without giving you the latest news about Halley's Comet. And we have got the very latest news. At La Palma, in the Canary Isles, John Beckman, Mark Kidger, and Mercedes Priola have been using the 100-inch Isaac Newton telescope to study the comet, with very interesting results. And they very kindly sent us their latest picture. Here it is. That black strip, of course, is purely an instrumental effect. But the really interesting thing there is the size of the comet's head. The diameter is something like 600,000 miles, more than half that of the Sun, and that is very much more than had been expected, so the comet is getting active. It's also now well within amateur range, and I've been sent a photograph by Mr. J.R. Fletcher of Gloucester, and there it is, the comet's shown between those two markers, and that was taken with an 8.5-inch reflector. And by this time next month, the comet should be an easy binocular object, and of course we'll keep you very fully informed. But for the moment, I want to turn to something entirely different. The main autumn constellation is Pegasus, and you'll see it now high up in the southern sky after sunset. And the main stars make up a well-formed square. And if you look, even with the naked eye, you'll notice that the upper right-hand star of the square, which is called Scat, is decidedly orange in color, whereas the other three are white. Now, one star of the square, Alpheratz, has for some unknown reason been given a free transfer into the next-door constellation of Andromeda. And in Andromeda, the most interesting thing by far is the great spiral galaxy M31, Messier 31, which you can just about see with the naked eye and very clearly with binoculars. Now, this is a photograph of M31 that I took the other day. It's that fuzzy thing slightly to the left of center. And I suggest it might be a good idea to take some practice photographs of it now, because Halley's Comet also is a fuzzy thing, and M31 is very good practice. Below the square of Pegasus, we have the rather ill-defined and faint zodiacal constellation of Pisces, the fishes. Nothing very much there, except, of course, that during December, when Halley's Comet will be at its best, it'll be tracking down through Pisces. But also in the constellation are two very interesting things you're not going to see with a small telescope, because they are extremely faint. There are two galaxies, NGC 7603 and 7603b. NGC, incidentally, stands for New General Catalogue, although by now it certainly isn't new. It was completed nearly 100 years ago. Now, these two galaxies lie side by side in the sky, and if you look, you will see they appear to be connected by a kind of luminous bridge made up of stars and gas and dust. And there seems from that picture no doubt that those two galaxies really are connected with each other. But are they? This is where I'm delighted to welcome back Iain Nicolson. And Iain, I think it's your turn now to tell us about the redshift and the Doppler effect.
Yes, I think the key to understanding these galaxies is the familiar idea of the redshift. If we think about light, we can think of it as a kind of a wave, and the different colors of light correspond to waves of different wavelengths. If we take light from a star or a galaxy and split it up into its constituent wavelengths, then we get the familiar rainbow band of color, the spectrum, together with a pattern of dark lines produced by atoms absorbing in the atmospheres of stars. Now, if a source of light is moving away from us, then the wavelengths become stretched. And so this affects not only the wavelength of light, but it affects the wavelength of the dark lines too. So the dark lines are moved towards the red end of the spectrum, and we say there's a red shift. If, on the other hand, the source of light is coming towards us, the light waves are squashed, and the dark lines are moved to the blue or shortwave end of the spectrum. Now, the amount by which the lines are shifted, the amount of the redshift, depends on how fast a star or a galaxy is moving from us.
And therefore, the speed of recession is a function of the distance. And by now, we can see galaxies out to thousands of millions of light years. But we also have those remarkable objects, the quasars, which look much smaller than galaxies, but are very much more luminous, and all of which have tremendous redshifts.
Yes, we can see the effect of the redshifts on the spectrum of a galaxy or a quasar by looking at a few examples. If we look at a fairly nearby galaxy, like Centaurus A, which is only some 16 million light years away, then the lines in the spectrum occur more or less at their normal positions. And the ones that are represented here, there are 3 lines in the visible part of the spectrum due to the element hydrogen, and 1 line known as Lyman alpha, also due to hydrogen, off to the left in the ultraviolet part of the spectrum. As we move out to a more remote cluster of galaxies, the Coma cluster, the redshift is only about 2%, but we can just begin to see the lines shifting from their normal positions. As we go out to the quasar 3C273, then we're dealing with a redshift of 16%. which seems to mean that that quasar is rushing away at 16% of the speed of light, and one of the lines that was in the visible, the hydrogen alpha line, has moved to the right into the infrared spectrum. As we go to the much more remote double quasar, all the visible lines have moved into the infrared, and finally, as we get to the extremely remote quasar, PKS 2000-330, even the ultraviolet line has been moved into the visible part of the spectrum. And so we see when we're looking at quasars that the spectrum of a remote quasar looks utterly different from that of a galaxy because of this enormous red shift.
And it seems that PKS 2000-330 is something like 13,000 million light years away. But it all depends on the red shift. And if these red shifts are not Doppler effects, then there's a very serious error. And there are one or two very well-known astronomers, as you know, who just don't believe this. Sir Fred Hoyle is one. He doesn't believe that the red shifts are Doppler effects, and therefore he considers that the quasars are not very far away from the edge of our own galaxy. And if so, well, that's going to cause a tremendous revolution. So what's the evidence, Ian?
Well, if we go back in time a bit, the first man to investigate redshifts and how they're related to distance was, of course, Edwin Hubble in the 1920s. And what he discovered was that the greater the redshift, the more remote the galaxy. And this relationship we now call the Hubble law. And quite simply, if we look at galaxies at greater and greater distances, we find they're receding from us at greater and greater speeds. And in fact, we can pick out some of the ones that we looked at earlier. We see that Centaurus A is moving away really rather slowly because it's only some 16 million light years away. The Coma cluster, some 400 million light years away, is still moving really at a rather modest speed. But by the time we get to 3C273, or the double quasar, then we're dealing with quasars that are rushing away at a large fraction of the speed of light. And of course, as you mentioned, PKS 2000-330 is rushing away from us at something like 92% of the speed of light, which according to the Hubble law places it at something like 13,000 million light years distance. Well, of course, people have argued as to whether the quasars really are at that sort of distance. And one of the observers who looked most closely at this particular problem is Halton Arp of the Mount Wilson observatories. And of course, with so many quasars and so many galaxies, you must expect that occasionally you're going to see a galaxy in the foreground against a much more remote background galaxy, and the two will look close together in the sky. But Arp maintains there are far too many of these close alignments for it to be simply due to chance. For example, if we look at M82, the familiar violently disturbed galaxy in Ursa Major, Arp has picked out 4 quasars in a curving arc, and they're picked out in the picture here and numbered 1, 2, 3. The quasars are the little dots between the lines, and he would reckon that in this case and in many other cases there are far too many close associations. In fact, in his view, if you look at the total number of close associations between galaxies and quasars, then you'd need odds of billions to 1 against that happening by chance, unless there are perhaps 20 times as many quasars as we think. But the point is that the quasars that are close to the galaxies seem to have very much larger redshifts than the galaxies. However, other people looking at the same problem with a different statistical approach come to the conclusion that there's nothing really surprising about these associations at all. And it just shows that really you can do almost anything you like with statistics.
Yeah, true.
But on the other hand, Arp has gone further than this, and he's found numerous examples of ordinary galaxies close together in the sky, which seem to have different red shifts. Now, for example, Jack Silentic of the University of Alabama has looked at a number of little groups of galaxies, quintets and quartets. A well-known one is Stephan's quintet. And it looks here like 5 interacting galaxies. And yet, one of them, the brightest of the group, has a redshift only 1/6 of the rest. Another example is Seyfert's sextet. Here we've got what looks like 6 galaxies, pretty close together and interacting, and yet the spiral, the one just to the right of center of the picture, has a redshift twice as great as its companions. That would, on the ordinary way of things, suggest it's twice as far away as the rest. Perhaps the most peculiar example of all is VV172, a chain of 5 galaxies. They look as if they're connected, and yet the one second from the right has twice as great a redshift as the others. Again, the conventional view is that that galaxy is twice as far away as the others. But Silentic claims that from the number of such little groups that there are in the sky, you would expect at most just 1 close association between a background galaxy and a foreground quartet or quintet. Now, there are at least half a dozen known, so maybe that's a little suspicious. But there aren't enough examples of this kind of thing to cast really serious doubts on the redshift. However, ARP has come up with quite a lot of examples of pairs of galaxies which seem to be physically touching each other. And if they are, and if they've got wildly different redshifts, this is a bit of a problem.
Which brings us down, of course, to our pair of galaxies and Pisces.
But of course, that's true, but we have to decide, really, haven't we, whether it's a real connection or a line of sight effect. Are we dealing with two galaxies which really are physically connected to each other, so that if we moved off to a different point in space and looked at them, we would see clearly that they're still connected? Or are we dealing with a pair of galaxies which is quite simply a line of sight effect? If we went off again to a different point in space, we would begin to see quite clearly that we're dealing with two wildly separated galaxies which just happen to lie in the same direction as seen from the Earth. Now, as you say, the pair in question, NGC 7603 and 7603b, do look very much as though they're intimately connected to each other.
They do.
In fact, they look remarkably like the well-known familiar galaxy M51, the glorious whirlpool galaxy, which, as you can see here, is a very fine spiral which is obviously connected to its rather disturbed companion by a long looping arm of stars, gas, and dust. And there's no problem with M51. We know that we're dealing with two galaxies roughly 20 million light years away, and they are physically connected to each other. But with NGC 7603 and its companion, again, looking at this negative print where the galaxies appear as dark blobs, it looks very much, as ARP said, as if the spiral arm extending from the main galaxy terminates precisely on the companion. And yet the companion has got a redshift twice as great as the main galaxy. On the conventional view, that would place it some 500 million light years further away, and it couldn't possibly be connected. Well, this particular example has been looked at very closely by Dr. Nigel Sharp, a British astronomer based at the Kitt Peak National Observatory in Arizona. And what he's done is to take 6 different negatives and to expose them all onto a single negative, and so produce a much enhanced image that we see here, and you begin to see that there's a lot more structure to the main galaxy than was first thought. And the spiral arm that seems to be connecting the two seems to extend rather beyond the companion. And in fact, Sharp looked at this another way. He scanned the main plates electronically and then digitally added the information together to produce a much deeper and richer and more contrasty image. And as we can see here again, the main galaxy, NGC 7603, has got a lot of structure, a lot of arms coming out of it, and it does look very much from this image as though what we're dealing with is a remote background galaxy, and we've just got a spiral in the foreground whose arms happen to pass across in front of it. There's no sign of any great disturbance in the apparently connecting arm, and all of it seems to suggest that we really are dealing here just with a case of coincidence, but there's not, really hard evidence.
So all a bit circumstantial. What about any observational tests to decide whether Galaxy B is the further away of the two?
Well, ideally, of course, what you'd like to do is to measure the distance of both galaxies independently of the redshift. But it's really very difficult indeed to measure the distance of a remote elliptical galaxy, unless you're very lucky and something like a supernova pops off to give you a standard candle. But there is one test that can be applied, and that's to look at something known as the velocity dispersion. If we look at the spectrum of an ordinary star, then we see, as you can see here, that the dark lines are pretty sharp and narrow. But if we're looking at a galaxy, if we're looking at the heart of a spiral galaxy, or if we're looking at an elliptical galaxy, then of course the spectrum is made up of the combined light of billions of stars, all milling around in different directions, some approaching us, some receding. And the spectral lines from the approaching stars will be blue shifted, those from the receding stars will be red shifted, and in the spectrum of the galaxy the lines become smeared out into broad lines rather than narrow ones. And by measuring the width of these lines, we can measure the so-called velocity dispersion, the range of speeds at which the stars are moving. Now we can use that information to measure the mass of the galaxy. We can also use that information through something that's known as the Faber-Jackson relation to find out the true luminosity of the galaxy. The broader the lines, the more luminous the galaxy. And if we know how much light the galaxy is emitting, and we measure how bright it seems to be in the sky, then we can work out how far away it is. And in fact, Nigel Sharp applied this test to NGC 7603, but unfortunately the errors in the observations were so large that really the results indicated either that the small companion was at the same distance as the main one, or it was twice as far away. So it's not too conclusive.
Not very helpful.
Not very helpful in a sense, And although it looks very much from Sharp's results as though the small galaxy is a remote one in the background, there isn't enough concrete evidence to rule out ARP's connection.
Well, are there any other candidates?
Well, there are quite a few candidates that ARP has produced, and another of his best cases is a galaxy known as 0213-2836, and here we see it. Now, this is, again, a spiral galaxy, and as you can see at the bottom left of the galaxy image, there's a spiral arm that snakes off and connects with another galaxy. We'll call that Galaxy A, whereas up at the top there seems to be another dark blob, which itself is a galaxy, and off to the right of that dark blob is what ARP described as a jet of material. ARP claimed that this jet of material was being torn from the little galaxy due to the gravitational interaction with the main one. But the point about it all is that that little galaxy B has a redshift twice as great as the main one, and should, on conventional views, be twice as far away. Well, Sharp looked at this one very closely, and he comes to the conclusion that that jet is not a jet, that it's actually a spiral arm crossing in front of the background galaxy, whereas the one at the bottom, the spiral arm there, which connects to the galaxy at bottom left, is a real connection, but those two galaxies have got the same redshift. If we sort of zoom out from this picture and look at the broader view, Sharp has found that there are several other background galaxies which have the same redshift as Galaxy B, and it seems pretty clear in this case that what we're looking at is a small group of galaxies with the main galaxy and its companion in the foreground, and there's no problem with the redshift.
What about a galaxy and a quasar embedded in it, or apparently?
Well, that's a very peculiar example. It was first looked at in 1971, and it's a problem that's refused to go away. What we see, if we look at the main galaxy in this false color image, off to the right of the main galaxy is a little blob, which is a quasar Markarian 205. Now, it's got a redshift 10 times greater than the main galaxy, and yet it seems to be connected to the galaxy by a bridge of material. A lot of astronomers have looked at this. Some maintain the bridge doesn't exist, some maintain it's a photographic artifact, others that it's due to a convenient interposing galaxy that makes the connection. But Jack Silentix looked at this, and he's quite convinced that the connection is real and can be traced into the heart of the main galaxy. If that's true, and the redshifts differ by a factor of 10, then the whole redshift business has got a major problem.
It really is a problem. On balance, what do you think? Are the redshifts red herrings or aren't they?
Well, the Hubble law seems so good, and it fits in so well with our ideas of the Big Bang and the expanding universe and the age of the universe and the scale of the universe, that really it's very hard to believe that it's not valid. And I suppose I believe in it every day of the year except February the 29th. But we have to admit that there are some cracks in the foundations, and it would be extremely exciting, I think, if we found a situation where our whole basis of cosmology was undermined.
With the greatest upheaval in astronomical thought for well over half a century. We've got to wait and see. Iain, thank you very much. Now, back very much nearer home, something very interesting on October the 28th, a total eclipse of the moon, when the moon goes into the Earth's shadow. And here's a photograph of the partial phase. You can see the shadowed part very clearly indeed. Now, this is going to be a total eclipse. The moon will rise partly eclipsed. Totality will begin at 1720. That's 520, because we'll have gone back to wintertime by then. Totality ends at 1804, and the whole eclipse ends at 1929. And although lunar eclipses are not important, they're very lovely, and they're certainly worth photographing, so do have a look on the evening of October the 28th. Our next program, on Tuesday, November the 12th, is going to be an extended special about Halley's Comet, so I hope you'll be able to watch that. And meanwhile, our latest newsletter's ready, so if you want it, as usual, send a stamped addressed envelope to this address, newsletter number 19, The Sky at Night, BBC TV, London W12 8QT, and we'll send you your newsletter. And so, until our special Halley's Comet program on November the 12th, from Iain and myself, good night.
And in the series Observatories of the World on Friday evening, Patrick Moore visits the world's most unusual observatory. It's a mile below the Black Hills of Dakota. That's on BBC 2 at 7:10 on Friday evening.